Hello everyone, welcome back for the lecture of theory of computation. In our previous lectures, we have seen finite automata, infinite automata, we have seen what is DFA and NFA and push down automata and minimization of DFA, and we have seen many more. And today in our lecture, we are going to see grammar and context-free grammar. First, we'll see what is grammar. A, a grammar is required to generate a proper sentence. So without a grammar, you cannot write a proper sentences. So similarly, same way in a theory of computation, we are using grammar to generate a proper language. So a language is a set of strings, a possible strings. It is a collection of strings to generate a language which can be applied by using a grammar. So grammar is a set of prediction rule which is applied for generating a string in a language. There are different types of grammar. One is unrestricted grammar, regular grammar, context-free grammar, and context-sensitive grammar. And now here we are going to see context-free grammar. Context-free grammar generates a language with the four tuples. That is VTPS, non-terminal symbol, terminal symbol, prediction rule, and start symbol. Okay, what is terminal? Terminal is the symbol for an alphabet being used. It might be a binary alphabet such as zeros and ones, and lowercase alphabets A to Z, and decimal alphabets 0 to 9, and many more. So generally, lowercase alphabet is used for an non-terminal symbols, not the uppercase alphabets, and non-terminal symbols, those are the variables which produces terminal in turn. So we cannot leave just as a non-terminal to generate a string. That non-terminal should be replaced with a terminal by using a production to form a strings to generate a language. So usually uppercase alphabets A to Z can be used for non-terminal symbols. And non-terminal symbol is same like a set of states in the finite automata. Okay, here start symbol. Start symbol is a special non-terminal where we begin our replacing our predictions. So here starts you can see a start state in our finite automata. Same in a, like a start state. Here we use start symbol. Okay, and prediction rule is the replacement rule of a variable where we generate a string. Okay, when we see an example, you can easily understand how to write a grammar and how to write a language with the help of grammar. We can, with the help of grammar, we are able to generate a string and a language, and with the language, we are able to write a grammar. Okay, here the grammar is given, we are going to generate a language. Okay, consider a terminal, which is A, and non-terminal S, and the start symbol is also S, and the protection rules are here. S turns to AS and S turns to A. So this is given S turns to AS and S turns to A. So the S turns to AS and S turns to A is the protection rule. Here, so we can replace for S, we can replace with AS or A. So let's begin. S turns to AS. So we can use any of the protection. So let's begin with applying the rule one, that is S turns to AS. Okay, again, so if we want to generate again, so S turns to, this S is again replaced with, S can be replaced with AS. So we are, S can be replaced here. Again, this S can be replaced with A alone. OL. So we'll generate a string called ye. So the rule 2 is applied to generate a string. Same thing. Again, we can use just S turns to A alone. So ye is the string which is replaced. And suppose we got triple A, and now we want to generate many other strings. So we can consider S turns to AS. Again, this S can be replaced with AS. And next, if you want to generate other string, AA, and this S can be replaced with AS again. And again, if you want to replace this S with A, So you can replace this S with A. So we have generated a string with 4A's, and we can generate a string with single A, 2A, 4, triple A, 4A, and so on. So these are the set of strings which is generated for a certain grammar. And from these strings, what can you understand? It is a string which is any number of A's. So therefore, we can finalize that a language here, that is the production with the help of production rule, we are able to generate a language of a power n where n is greater than or equal to 1. 1 is or more than 1 is. So this will be our language for the production rule, which is, and now we have a language. Now we are able to write a grammar for that. So here it is given a grammar, construct a grammar for a language a power n where n is odd. But in our previous example, we have seen any number of a's. There is no odd a's or even a's. It can be 1a, 2a, 3a, and 4a, and so on. But here it is odd number of a's. So 1a, 3a's, 5a's, 7a's, and so on. So for we should write a common grammar which is able to generate a odd number of a's. So only then our grammar is correct. So here, so when n is 1, a single A is generated. When n is 2, triple A is generated. When n is, n is 3, triple A is generated. When n is 5, 5 A's are generated. Okay, so let's write a prediction here. So let's begin S as the start symbol. Okay, so S turns to, so when we want to generate a mm, single A, so we can write a prediction called S turns to A. Okay, that's it. And suppose if you want to generate triple A's. So what can be protection used? So yes turns to ASA. S turns to ASA. So this S can be replaced with a previous production. So here when you apply S turns to A, so you'll get A. So when this S is replaced with A, so we are able to get a string called A and A. Okay, same thing. Again, this S turns to ASA can be applied to generate more odd number of A's. So these both production is enough to generate a language with A power n where n is odd. So S turns to A and S turns to A is sufficient. So what is our grammar here? Here you can see. So our production is S turns to A and S turns to ASA. And our grammar is, so only V is the non-terminal. So S is the non-terminal and A is the terminal here, which is the terminal which is used, A. And what is the production? This one. And S will be a start symbol. A start symbol is also S. So they generate a grammar from the language which is given. So this is how we write a language or we write a grammar. So I hope you have understood. So we can solve many other examples in our forthcoming lectures. Is what do we mean by derivation? So we are generating a string, but there is certain rule to be applied to generate a string. It might be it is the sequence of grammar rules for transforming the start symbol into our string. So the rules which apply is leftmost derivation and rightmost derivation. So here you can see what is leftmost derivation. Leftmost derivation, the input which is scanned is, starts from the left to right. So replacement of a non-terminal should begin with left. And in the rightmost derivation, the replacement of the non-terminal should always start with right hand side. That is rightmost derivations. So by seeing an example, you can easily understand what it is. So the production which is given is S turns to S plus S turns S star S and S turns to X or Y or Z. So you can use any of this production of X. So based on the input which is given, you can use AD production to get up the string. Okay. So here you should generate a string called X star Y plus Z. So that can be written as, so suppose let's consider, yeah, S turns to S plus S or S plus S. Okay, so for that, so we need a plus as well as star. So again, this S can be replaced with, again this S can be replaced yes star s, which is given in the protection. So we have a star here and we have a plus. Okay, so our string, the input which is given, star and plus is correct. Okay, now we are using leftmost derivation. So if you have a non-terminal here, S is also non-terminal, here is also non-terminal, but we should generate X, Y, and Z. So the replacement of the symbol should begin with the left side. So which on the left hand side, S should be replaced first. So this S can be replaced with, so you can see here, X or Y or Z. So this can be used here. So yes can be replaced with first X. Okay, then you can leave as such. And in the next step, you can use yes can be replaced. So here we need Y. So this S can be replaced with Y. Okay, that's it. And next in this S, so we need Z. So this S can be replaced with Z, which is given in the protection. In the protection, instead of S, we can use X, Y, Z, or S turns to S plus S, or S turns to S star S. So the replacement of the non-terminals begin from the left-hand side. So this is leftmost derivation. And same thing you can see in the rightmost derivation. The derivation, the replacement starts from right to left. So similarly, here you have been given with this protection. S turns to S star S, S plus S minus S, and S turns to X, Y, and Z. So same thing, the input is given. So for this input, yeah, we are going to generate. So we need a minus and then star. So you have these star and minus. So you can replace with anything. S turns to S minus S. Then again we need star here. So this S can be again replaced with, and this S can be replaced with S star S. Okay, so we got minus and star as given as the input. Okay, now we need x, y, and z. So it is rightmost derivative. So we should start the replacement of the non-terminal from the right hand side. So first, this s is replaced with, so we need z. So it is replaced with z. And next, this in these two non-terminal, this is the right hand side. So this s is replaced with y, and next this s with replaced with z. So finally we got the input which is given in the example. So these are the derivation which is applied to generate a input. Okay, so that's all about our today's class. Thank you. We'll see the next session in the other lecture. Thank you for watching this.